All right, so now we're going to have Johanna Bimmermann from Bochum also, who will tell us about capacities of disk tangent bundles of symmetric R-spaces.
So thank you very much, Vinicius. Thank you so much for the invitation. I'm really happy to be here in this lovely city, in this lovely institute. Yes, and today I will present my most recent research. It's actually so recent that it is not yet in the archive, and this is kind of the first time I talk about it. So yeah, if there's anything you don't understand, it might be because it's not completely well organized yet. So I hope it goes well. So interrupt me at any time there's anything unclear. Okay, so yeah, symplectic capacities are invariants of symplectic manifolds. So I will give a bit of background on symplectic invariants. So to start with, we have a yeah, symplectic manifold. No restrictions so far on the manifold. And symplectic means that omega is a 2 form, right? On M that is closed and non-degenerate. Where n, I think I put it, is half of the dimension of the manifold. And now this closeness assumption, in a sense, can be read as an analog of flatness, in this, if we want to compare to Riemannian geometry, which leads to the so-called Dabou's theorem, which tells us that all symplectic manifolds are locally the same. They locally, you can express the symplectic form locally in terms of yeah, the standard symplectic form, which means we do not have any local invariance, just in contrast to what we have in Riemannian geometry. So the question for symplectic invariance is a global question. And globally, we do have a first very obvious choice of an invariant, which is volume, right? So since our symplectic form is non-degenerate, if we integrate yeah, the top power, we will get a number that is invariant under symplectomorphisms. And symplectic capacities are yeah, another kind of symplectic invariance measuring roughly the size of a symplectic manifold. And they were born with the so-called, or with the famous Gromov's non-squeezing theorem that tells us if we try to embed symplectically the ball, or yeah, the standard ball of radius little r into the cylinder of radius big R, where it is kind of important that we choose a pair of coordinates that is symplectic, spans a symplectic subspace. That this only, or this works if and only if, oh, okay, I don't know how this pointing works exactly. If and only if the radius big R is bigger or equal to the radius little r, which means that volume is usually not a good obstruction for symplectic embeddings, right? So we are looking for invariants that give us a better way of abstracting symplectic embeddings, and yeah, this is symplectic capacities. So a symplectic capacity assigns to a suitable subset of symplectic manifolds of dimension 2n, yeah, a real non-negative number, according to the following rules. That is one. Scaling, if we scale the symplectic form, the capacity should scale. Monotonicity, if we embed a symplectic manifold into the other, then the capacity of the first should be smaller than the capacity of the second. This also gives us invariance under symplectomorphisms, of course. And then last, this one is not always required, but for this talk I will always assume it, is normalization. So the capacity of the ball is the same as the capacity of the cylinder. And yeah, all three, so if we can find such a capacity, all these axioms together actually also imply Gromov's non-squeezing theorem, which means existence of a capacity is already a very strong statement. Okay, so what are examples of symplectic capacities? The first one follows out of Gromov's non-squeezing, in a sense. We can simply ask for the largest ball. I don't know. Okay, I think I I'm pressing the wrong. Okay, we can simply ask for the largest ball that embeds symplectically in our manifold. And this will give us a symplectic capacity. With this very first capacity, we can already say a few things, namely, we know by Darboux theorem that always a small ball embeds, right? A ball of radius epsilon, let's say. So the Gromov width will always be bigger than 0, so never 0. And then, because we have this monotonicity property, all other capacities, or monotonicity and normalization, all other capacities will be bigger or equal to this first capacity. And then there's another symplectic capacity I want to mention here that is defined a little like, I only put a very rough definition. That is called the Hochverzehner capacity. It very roughly, it measures, like if you have a Hamiltonian on your symplectic manifold, then you kind of expect that if you scale the oscillation, make it bigger and bigger, that at some point periodic orbits or fast periodic orbits appear, where fast means period less than 1. So this capacity measures how much a Hamiltonian can oscillate before you have fast periodic orbits on your manifold, if you have any. And now with these two examples, and there are plenty more, you can also define an analog of the systolic ratio. I mean, these capacities are kind of the symplectic analog of maybe a spectral invariance or something, so it makes sense to compare them to volume. And I think we saw this already a little bit in Alberto's talk. So we can study this ratio and ask, for example, if it is finite for a suitable subset of symplectic manifolds or whatsoever. And maybe note here that two things: if the capacity is the Gromov width, then or any other embedding capacity, then we do know that C must be less or equal than 1, because we cannot have a symplectic embedding that is not volume preserving, right? However, if the capacity is the Hochverzehner capacity, for example, and we just take the full class of symplectic manifolds, there's certainly no such bound, because that's a very nice result by Usher. Many closed symplectic manifolds, so manifolds with finite volume, actually have infinite Hochverzehner capacity. So for such a class of manifolds, the question does not make so much sense. But eventually, if you restrict your class of manifolds, then it could be an interesting question. Now, the class of manifolds I want to discuss here are so-called disk tangent bundles. Maybe note first, why not the full? So, maybe the more natural class to study would be cotangent bundles, full cotangent bundles. But we already see. I mean, you can kind of always embed the product of the Lagrangian product of a ball of small radius times Rn. Using the exponential map, in a sense, in the first factor, and then just fiber-wise, or this identified with the tangent space at a point, into a cotangent bundle. And such a Lagrangian product will have infinite Gromov width, because we can squeeze in a ball of arbitrary size. So a full cotangent bundle will always have infinite capacity, or any capacity. This is why we need to restrict to some subsets of cotangent bundles. And a nice choice, I would say, are disk tangent bundles. So we fix a metric on the base manifold, I denoted by G here. And then we look at the associated disk tangent bundle. And since we fixed a metric on the base space anyways, we can identify cotangent bundle and tangent bundle, and then work in the tangent bundle, which I personally find easier to visualize. This is why I always do things with the tangent bundle. Okay, so maybe a few observations why this is an interesting class of symplectic manifolds. First of all, disk tangent bundles are sublevel sets of the kinetic Hamiltonian. The kinetic Hamiltonian generates geodesic flow, which means the boundary, the Reb orbits in the boundary of the symplectic manifolds are actually lifts of geodesics. So we expect a relation to Riemannian geometry for this class of symplectic manifolds. Then second, and yeah, I think like there should be a scaling if I don't do like if I do arbitrary radius. So let's say R is 1. Then the symplectic action of a Reb orbit will coincide with the length of the geodesic on the base manifold, which means that if we, I think experience shows that we can kind of expect our capacities to be somewhere in the action spectrum. So we see that eventually for this class of manifolds, our symplectic systolic ratio might have something to do with the systolic ratio introduced by Alberto earlier, and I think we already saw the case of the tangent bundle. And then the second thing, of course, is that the volume of the disk tangent bundle also has a relation with the volume of the base manifold, the Riemannian volume. So indeed, a symplectic systolic ratio here would have implications for the ordinary symplectic, or could have implications for the ordinary systolic ratio. Now, when it comes to compute, when it comes to computing capacities of these disk tangent bundles, actually there's almost nothing. No, we only know a handful examples, I would say. The first computations are actually by Vinicius Ramos, Brian Ferreira, who are here, and are for spheres, RP2, Zoll spheres, and some spheres of revolution. And then I did some computations in my PhD thesis, which was RPN, CPN, Hermitian symmetric spaces of compact type. We were also able to do flat tori and length spaces. But apart from this, you see, it's a list of examples. So at the point any new capacity is interesting, so that eventually we can see if they have, if there's some general scheme behind this. Yes.
The camera guy is asking if you could take your microphone
Yeah.
out of your pocket.
Sure. But where should I? Okay. This one. Okay, I see. Absolutely. Okay, perfect. Thank you. No worries. Okay. So how do we get explicit values for disk tangent bundles? We already saw that the capacities I was talking about are always defined as supremum over something. So generally we find a lower bound and the upper bound individually, compare the two, and show that they agree. For the lower bounds, recall that they were always defined as supremum. We use some explicit constructions, either of embeddings for the Gromov width, or constructions of admissible Hamiltonians for the Hofer-Zehnder capacity. In the examples that I showed you previously, maybe you noticed that all of them have a lot of symmetry in a sense, which indeed is helpful for both scenarios. For example, if the geodesic flow is integrable, which is the case for what Vinicius and Brian did, for spheres, round spheres, RP2, and Zoll spheres, and also spheres of revolution, you may be able to find, or you have enough integrals of motion to detect what I would like to call hidden toric domains. And into toric domains, we understand embeddings of balls very well. So this is how you can eventually find balls hidden inside a tangent bundle. And then for the Hofer-Zehnder capacity, this is a bit more what I did. Is if you start with the Hamiltonian, and that is in a sense just a reparameterization of the kinetic Hamiltonian. You will get a Hamiltonian that is not smooth at the zero section and also not like compactly supported, but after a small modification, so it's at the moment rather V-shaped, but you can kind of modify it a little bit near the zero section and near the boundary to get something admissible. Yeah, you see that all periodic orbits of those are periodic geodesics, and if the systole denotes the length of the shortest geodesics, this Hamiltonian will have periodic orbits of periods of periods 1 or bigger. So this is why this kinetic Hamiltonian is a good starting point to construct admissible Hamiltonians. Also, we see that on the disk tangent bundle, unit disk tangent bundle, this has oscillation exactly the systole. So as a first lower bound for the Hofer-Zehnder capacity, we always get the length of the shortest closed geodesic. And then, but there are situations where this lower bound is simply not good enough. So strategies to increase this lower bounds may come from billiards. So playing Riemannian billiards on an suitable open subset of your base manifold. Eventually, you can also destroy some families of closed geodesics by adding small exact magnetic perturbations. This is what we did in the case of lens spaces. So there's a lot of playground, is what I want to say, to construct nice admissible Hamiltonians. And then for the upper bound, we always use holomorphic curves, pseudo-holomorphic curves in one way or the other. I will not get into it. This is abstract black box for this talk. In the work by Vinicius and Brian, it enters in this with some sort of symplectic homology or embedded contact homology rather. And for what I do, it enters in terms of non-vanishing Gromov-Witten invariance. So my strategy is rather to embed the disk tangent bundle into a closed symplectic manifold. If this closed symplectic manifold has holomorphic curves going through every point, we by this theorems, or I can press something wrong. Okay, by this huge theorems of Gromov, Hofer-Viterbo, and Lu, able to deduce from non-vanishing Gromov-Witten invariance upper bounds to Gromov width or Hofer-Zehnder capacity. Okay, so let us maybe see how this works in 2 examples. This is also historically more or less the first 2 examples that show up. So I already mentioned this very nice result, which computes the Gromov width of the unit disk tangent bundle of CP1 with the round metric and RP2 with the round metric. And systole is a strong word here. Of course, both of them are Soll metrics, so it means it's the length of a simple closed geodesic. And in this case, both geodesic flows are integrable. So you have the kinetic Hamiltonian and an angular momentum, which make it integrable, and you can actually use this to get some to find some hidden toric domains, which in the case of CP1 is if you remove the fiber over a point, you find that the space is symplectomorphic to the symplectic byproduct of 2 disks. Where we can easily embed a ball, just diagonally, a ball of radius square root 2. And then Vinicius and Brian used ECH capacities to show that this embedding of the ball is actually optimal. And for RP2, there's a similar toric domain, just that now we need to remove a totally geodesic copy of RP1, and then we get a 4-ball. Observe that this 4-ball is already volume filling, so you don't need to work much harder to see that it's the optimal embedding. Now, I kind of took the opposite approach. Instead of embedding a very nice symplectic manifold, I embedded my disk bundle into nice symplectic manifolds, which in the case of CPN is, you can show that the disk disk tangent bundle of CPN is actually symplectomorphic to the product of two CPNs with the standard Fubini-Studi form, and a symplectic divisor, so codimension 2 symplectic, closed symplectic manifold removed. And from here, it's maybe easy to believe that holomorphic curves in the product are well studied, so we can obtain upper bounds for the capacities now in terms of holomorphic curves on the right-hand side, right? For the lower bound, for example, of the Gromov width, we need to work a little bit harder because it's not too hard to embed a ball symplectically into the product CPN times CPN. Just view it as the completion of the ball times the ball. Then again, I mean, the pictures are kind of similar to each other, right? If you compactify the guy above here, you suitably you get the guy below, right? So you can show that in this case it's actually true that the ball you embed into the product here already sits in the disk tangent bundle. I put the term Hamiltonian circle action here because in the more general setup of Hermitian symmetric spaces, which we will have in a minute, you can identify the ball as a sublevel set of a Hamiltonian generating a circle action. And then for RP2, there's RPN, there's a very similar identification. You can put the unit disk tangent bundle of RPN into CPN, where you remove the complex quadric of one dimension less. In this case, the ball that obviously embeds into CPN does not lie in the complement of the quadric. So you will, you will need to use some sort of holomorphic gradient flow, actually the gradient flow of precisely the circle action, to push the ball into the complement of the quadric. And because this flow preserves the hypersurface to be symplectic, you can show that you end up with a symplectic embedding of the ball, volume-filling ball into the disk tangent bundle of RPN. Then again, it's volume-filling, so you don't need to worry about the upper bound. And now, the main result I want to present today is a generalization of this result. For this, observe that in some sense, the product CPN times CPN is a complexification of the base manifold. So we have a Lagrangian embedding of CPN into the product by, in a sense, taking it would be easier to say if I put a minus here, then I can embed it diagonally and I will get a Lagrangian embedding. If I put a plus, I need to, for the embedding, I need to put an anti-holomorphic involution on one factor to see that you get a Lagrangian embedding. But in this sense, CPN is actually a real form of the product CPN times CPN, by which I mean it's the fixed point set of an anti-holomorphic involution on CPN times CPN. And similarly, easier to see, RPN is a real form of CPN. It's a fixed point set of an anti-holomorphic involution on CPN. And coming from this perspective, I was wondering what are the real forms of Hermitian symmetric spaces. So Hermitian symmetric spaces are compact homogeneous scalar manifolds, let's say. If you have an anti-holomorphic involution and a fixed point set of such, they will be Lagrangian submanifolds. And if you have Lagrangian submanifolds, you can always hope to embed, by Weinstein's tubular neighborhood theorem, a portion of the tangent bundle. And this is the starting point for what is called symmetric R-spaces. Symmetric R-spaces are precisely the real forms of Hermitian symmetric spaces. What is meant by the term symmetric R-space? So an R-space, or a generalized flag manifold, for me is really just the quotient of a non-compact semi-simple Lie group by its parabolic subgroup. This means the quotient is actually a compact homogeneous manifold. and it is symmetric if we can find a metric, or if it is also homogeneous for the compact, maximal compact subgroup of G, so that we get a second representation of N as a homogeneous space. So K will be the group of the isometry group, and G is somehow a larger Lie transformation group, which might be biholomorphisms if the manifold has a complex structure, might be conformal transformations on spheres, for example. The key point is that there's symmetric spaces are classified, and therefore also symmetric R-spaces are classified, but the list of examples includes many really nice examples, which is Grassmannians of any type, so real, complex, quaternionic. There are some compact Lie groups. There are quadrics, real ones, complex one, and then there are also, there's more, but there's also some exceptional ones, such as this Cayley projective plane, it is called. So definitely a nice class of manifolds to start with, if we only know the capacity in a handful of examples. This would be, I think, a good generalization of that. Now, how do we see that these symmetric R-spaces are actually real forms of Hermitian symmetric spaces? The idea is kind of simple, because you have this double representation as quotient. There's a natural way to complexify the story. You can either start with this non-compact group, complexify it, and then, because if you complexify a parabolic group, you get again a parabolic group. The quotient you end up with will be a compact space. Actually turns out to be a compact Hermitian symmetric space. While the story on the other side is different. You complexify a compact group, compact Lie group, and you can show that the complexification of a compact Lie group is, let's say, diffeomorph to the product K times the Lie algebra of K, which in turn can be identified with the tangent bundle of K. And this induces induces the fact that as KC orbit that is included in the GC orbit, we kind of get a copy of the tangent bundle inside of this Hermitian symmetric space. This embedding cannot be symplectic by any means, because the tangent bundle has infinite volume, and the Hermitian symmetric space has finite volume. But just a quick note: it can be made holomorphic. So if you fix the so-called adapted invariant complex structure on the tangent bundle, then this embedding is actually holomorphic. So the idea now is to kind of restrict to a subset of the tangent bundle, so that we can, by some sort of scaling in the fibers argument, make the map symplectic on the subset. Okay, and I think I have a note on the fact that this really gives us what I said before, that N is a real form of NC, namely if you integrate the anti-holomorphic involution on this complex Lie group, on this complex Lie algebra to this symmetric space, you get an anti-holomorphic involution fixing N, because N is lies inside of K, which is fixed by the involution. Generated by K. So there's this theorem by Takeuchi that says that this is actually an equivalent characterization of symmetric R-spaces, which was the starting point of why to study these spaces. Okay. In order to find this suitable subset of the tangent bundle, it is really helpful to give somehow a geometric realization of this inclusion as a real form. which can be done in terms of adjoint or co-joint orbits. Again, here there's a metric involved. So via the Killing form, you can always identify adjoint and co-joint action. We do know that this space NC is a Hermitian symmetric space, which tells us that we can realize it as a co-joint orbit. Maybe I draw a quick picture here, because that's explaining the idea better. If we take as example GV being SU2, which is isomorphic to R3, we can actually draw pictures. Then if we take the co-joint orbit of any point on the SU2 or SO3 action, we get the sphere, right? And now we have in a sense two Cartan decompositions of this Lie algebra GV. There's one that corresponds to the Hermitian symmetric space itself, and then there's another one that comes from this complexification story. And in the picture, we see this in the following way. So the K will just be rotation in the z-axis. So that indeed this real form is the K orbit, so the smaller group of the fixed vector. So it's so K now is rotating the real plane in a sense. So in this picture, this would be RP1, this would be CP1. And the anti-holomorphic involution is then really induced by the Cartan involution of this Cartan decomposition. So in this case, it reflects at the xy axis. So this is the tau. And now, I think I have this also as a slide, this picture. So maybe I go through this example one more time with the slide. Sorry, this was a little bit chaotic. So in the very easy example of RP1 being SO2, we see that RP1 is not only a homogeneous space for SO2, but also for SL2R, right? Which is a non-compact Lie transformation group acting on RP1, which is the space of, real lines in R2. And so when we complexify SO2, which is a circle, we get C star. And if we complexify SL2R, we get SL2C and quotient out the parabolic subgroup. So we see that in this picture, actually RP1 lies in CP1. And now the picture with the co-joint orbit is the thing I drew here. We can find this vector xi in the xy plane, so that if we take the SO2 orbit of it, then we actually get the space RP1. And if we take the full SU2 orbit, we get the space CP1. And the Cartan involution that corresponds to it actually reflects at this z-axis. So it's in coordinates written, it fixes the xy plane and reflects the z coordinate, so that we see geometrically that we get the anti-holomorphic involution on CP1, fixing RP1 by reflection at the xy plane. And now we wonder what are the orbits that, or what are the points that are not hit by this SO2C orbit. And in the picture, we see that these are really just the antipodal points S and N, which is what I put on the slide before. The set delta, so the points in NC, so that if we apply the anti-holomorphic involution, we get a point in the cut locus of A, so the locus where the shortest geodesic that connects it is not minimal anymore. And the claim is that this is precisely the set we need to cut out of NC so that we get the full tangent bundle. Okay. And yes, this is the point I wanted to make with this example. In this example, this is really just given for the points in S, because if I take any other point, I reflect it, I land, for example, here, and the shortest geodesic connecting these 2 points will be unique unless we are on the antipodal points. And then the second minimal example we need to consider is CP1. So CP1 has also this sort of dual description as homogeneous space. It's homogeneous for SU2, and the Kähler structure is invariant by that. And and also it has this SL2C action, which is a non-compact group. And again, we can complexify SU2 to get SL2C. And this is already a complex Lie group, so the complexification is the product. So we in this picture really again obtain the embedding of the tangent bundle of CP1 into the product. We can also try to visualize this in terms of coadjoint orbits. Now, instead of having 1 copy of the sphere, we have 2 copies. So we take we take 2 points, and the Lie algebra that has -1, or okay. So we reflect at the anti-diagonal copy of R3, and fix the diagonal copy of R. So again, we see that the anti-holomorphic involution is given by a linear involution on the Lie algebra. Okay. So maybe with these a little confusing examples, let us try to find out what is the sublevel set, or what is the neighborhood of the zero section that we can actually fit in symplectically into our Hermitian symmetric space. It turns out these are not always disk bundles. Actually, these are subsets that have a non-smooth boundary. They sit somewhere between squares and disk bundles, I would say. And that is in the following sense, that again is a little bit algebraic. So the point is that in a symmetric space, you have this notion of maximal flat submanifolds. These are algebraically characterized as so-called maximal abelian subalgebras. And we can, in these maximal abelian subalgebras, define a cube, which if we take the H orbit of these cubes in the tangent bundle, characterize an open neighborhood of the zero section that is in complex geometry usually referred to as Grauert domain. And this Grauert domain is precisely the subset of the zero section that we can fit into the tangent bundle, that we can fit into the Hermitian symmetric space. So this is the main theorem here, and should be read as generalization of what I showed you before for the disk tangent bundle of CPN and RPN. As for CPN and RPN, we kind of have two cases, which which is hidden in this radius R, because for some not so mysterious reason, but there's exactly two cases that can happen. The complexification can have the same rank or twice the rank of the original manifold. So what is the idea of proof of this theorem? The idea is that we in a sense, make a global version of Weinstein's tubular neighborhood theorem. Recall that the base manifold N really was inside our complex or our Hermitian symmetric space as Lagrangian. So Weinstein's tubular neighborhood theorem will give us a symplectomorphism of a small neighborhood of the zero section. And the idea is now to find a Liouville vector field on the right hand. I mean, we have a Liouville vector field on the tangent bundle, so that we can kind of shrink every neighborhood of the zero section into a small neighborhood on the into a small neighborhood of the zero section. So if we could find something similar on the other side that could also shrink everything into a small neighborhood of the Lagrangian, and a map that intertwines these two Liouville vector fields, then we can use them to also get the global statement. And this is the idea. This invariant Liouville vector field is actually not too hard to find, because we do know that the symplectic form on the Hermitian symmetric space with this antipodal sect removed is exact. Because I showed you it's diffeomorphic to the tangent bundle, so we can contract the complement onto a Lagrangian, which means if we integrate our symplectic form over any closed submanifold contained in the complement of this divisor, we can homotope it onto the Lagrangian where the symplectic form vanishes. So the symplectic form evaluated on any cycle vanishes, which means it's exact. So we do find a primitive, and K is a compact group, so we can average this primitive to make it K invariant. And now if we have a primitive, we can implicitly define a vector field, right? Which is a Liouville vector field, which is all we wanted. And then there's a computation in terms of Lie algebras that shows you that if we remember that this NC, let me put it here, we viewed it as a subset of GV, and inside here we have K contained. So this notion of projection makes sense, and we can show that this vector field here actually projects to the Euler vector field on this Lie algebra K, which is good news, because this is precisely what we need to show that we can shrink any using the flow of this Liouville vector field. We can shrink any neighborhood of the zero section. So in particular, the pre-image of a small open set containing 0 in here, to make it so small that we can intertwine it with some with some open neighborhood of the zero section. The mu Tn here, I didn't put it anywhere yet, but this is the momentum map for the action, the K action induced on the tangent bundle by the K action on the base. And okay, so we really can make it small and can make it big again, and obtain, in a sense, a symplectomorphism between the full tangent bundle and what I would call the symplectic completion of this complement of the symplectic divisor at infinity. And now what is left to do is to compare moment map images to see that actually this theorem holds true. And I will again only do it in examples. So here I finally write the formula for the momentum map on the cotangent bundle. Recall that here in the picture, okay, I think I have the picture also here anyways. So in the picture, P here is the xy plane, and the Lie bracket is the cross product. So if I take a point in the tangent vector, a point in the tangent space of RP1, and take the cross product of x and v, I really always land in K. This translates into the fact that this is actually this decomposition of the Lie algebra comes from a Cartan decomposition. So whenever you take the Lie bracket of a vector in P and a vector in P, you end up in the Lie algebra K. Okay, and in this in this little example, what we see is that the moment map image of the unit disk tangent bundle of RP1 is really, we obtain all vectors in R up to length 1. So we get in this direction 1 and in this direction -1. So the moment map image is actually the closed interval -1, 1. And then if we look at the symmetric space NC, which in this case is CP1, then similar story. The moment map is just projection onto this z-axis. So again, we get the closed interval -1, 1. Sorry, it should be actually open. I don't know why I put closed here. It should be open interval because we removed the anti-diagonal or the antipodal points, right? So we do not get 1, and the disk tangent bundle is also open, so it's the open interval -1, 1. And the general case is not so much harder because actually this moment map is equivariant with respect to this K action, this K action is transitive on maximal flats, and maximal flats are exactly spent by either this example or the example of the product that I have here. And then therefore, in both cases, either 1 or 2, these minimal examples already give us, in a sense, the full story. And so I will quickly explain also the second one. Now here, if you start with an arbitrary point in the tangent bundle of S2, and you take the cross product, you get another vector in R3, where if the sphere is normalized to have radius 1, then you will get a vector of length exactly the length of V. And if you move the point, you see kind of that this plane can point in any direction. So the moment map image you get here is really the full 2 ball, which on the other hand is precisely the same you obtain when you take the projection onto K, which in this situation would be the sum of the 2 vectors. It can be anything in the 2 ball, right? Like if it points in the same direction, you will get points of length 2. So also here you see that the moment map image of this is the same as the moment map image of this, and therefore the 2 sub-level sets need to be symplectomorphic. Okay. So in conclusion, we have now this very nice, okay, I don't know if the neighborhood of the 0 section is nice, but we see that this neighborhood of the 0 section embeds open densely into this Hermitian symmetric space, and these Hermitian symmetric spaces have the very good property that there are plenty of holomorphic curves, in particular non-vanishing Gromov-Witten invariants, which enable us to get upper bounds for the capacities we were aiming for. So we can actually compute the precise values of Hofer-Zehner capacity and the Gromov width of these weird-looking neighborhoods of the zero section. Yeah, the upper bound really, I mean, I put a little bit more information here. Maybe I try to go through it. So the key idea here is that on this Hermitian symmetric space, you have a very nice Hamiltonian circle action. Actually, in the picture of the polysphere, it's really just the diagonal circle action that rotates around one axis. And the circle action has the property that its minimum is an isolated point. And sublevel sets of such Hamiltonian circle actions up until to the next critical value are balls. In this case, we get a ball of radius square root of 2, I think. And in this way, we can embed balls into these Hermitian symmetric spaces. A priori, it's not so clear that they lie in the complement of this divisor at infinity delta, but one can use the gradient flow of this Hamiltonian, if in doubt, to push the ball into, or to push the divisor at infinity into the complement of the ball. And now, because this flow is actually holomorphic, we get embedding of the ball into, okay, here the moved diagonal, then we can pull back everything to get an embedding of the ball with a changed symplectic form. But this symplectic form has the property that this delta is still a symplectic submanifold of NC, so we can use a relative Moser trick relative to this set at infinity to show that this is again symplectomorphic to NC with this delta removed. So we do get an embedding of a ball of radius a little less than 2 into this Hermitian symmetric space, and this is how we can get a lower bound for the Gromov width on this side. And then for the upper bound, as I already mentioned, we use the fact that this is, that these curves are, these spaces are uniruled is not too hard to see because any S1 orbit of a gradient flow line of Hamiltonian here will give you a holomorphic curve through an arbitrary point. So you really have holomorphic spheres going through every point. Yes, which leads us to an upper bound with a suitable normalization. This then really gives you the correct upper bound for these cases. So now to finish the talk, I will talk a little bit about disk tangent bundles, which was the starting point. We know how to compute the capacity of these weird neighborhoods of the zero section. And we know that the disk tangent bundle of radius 1, let's say, always embeds into this weird neighborhood of radius 1. But if the rank of the symmetric space is not equal to 1, this is really just embedding. So it turns out that if n is simply connected, and this is rather case by case than anything else, that then this embedding is, we get okay. I need to show this theorem again. Okay, if n is simply connected, then this R here is actually 2. Okay, so we have a 2 here and a 2 here, and here we have twice the system. So we can embed the disk tangent bundle of radius 2 into this neighborhood, so that as upper bound from this embedding, we do get 1 time the length of the shortest closed geodesic. And then for the lower bound, we can really use this Hamiltonian to see that this is the precise value of the capacity of the disk tangent bundle. No, there's lots of other spaces like RPN and the real Grassmannians, where the space is not simply connected, we started with. And actually in this situation, a couple of things can happen. For example, if we look at the real quadric, which I wrote down here as a zero set of a polynomial in RP p plus q plus 1. And then, okay, complexification is the complex quadric. We do not have signature in the complex world, so it becomes a plus here. And it can be shown that this real quadric is actually isomorphic to the product of two round spheres, where we quotient out the antipodal, the diagonal antipodal map. And in this very example, we get another upper bound from the universal cover. The cover here is then SP times SQ. The disk tangent bundle of this thing sits in the product, DS1 in the product, which we can compactify to the product of two quadrics. And the upper bound we get from this embedding is actually stronger than the upper bound we get from the embedding I discussed before. So, okay, I will go. So the upper bound we obtain here is the square root of 2 of this system, which is the length of the shortest contractible geodesic. Maybe I can convince you in the last second of why this is. So if we look at closed geodesics on this product where we quotient out the Z2 action, then if we walk like diagonally from S to N, we get the shortest closed geodesic because S is identified with NN, right? In this picture will have I don't know. I mean, it's the picture is really that of a torus. So if you only walk in one factor, it's a little bit twisted. So this corresponds to walking diagonally, while the blue line corresponds to walking on the torus. So on the side of the torus. So indeed, this red line is longer than the blue line, but the red line is the one that gives us the upper bound. So we need to increase the lower bound in a sense. And we can do this by a billiard system, I would say. So we play billiards on the product of two upper hemisphere to get to actually double the length of these geodesics, but the length of this geodesic stays the same. So with this, we see that in this case, we get a value that is strictly smaller than 2 times the system what we would eventually expect from the theorem above. So the conclusion, and this is the last slide, is that okay, if n is simply connected, we can say that the Hofer-Zehnder capacity is actually the system. But if n is not simply connected, we get different things in different cases. For RPN, we get twice the system. For the real quadric, we get square root of 2 times the system, which is the length of the shortest contractible geodesic. So the question I want to answer until I upload the preprint is what is about the other cases. There's a few other spaces you can explore. Eventually write down some nice billiard dynamics or whatsoever to find good lower bounds and to see what the Hofer-Zehnder capacity of the disk tangent bundle in these cases is. Okay, so then thank you for your attention and with this I would like to finish.